In this video, we are going to look at ideals of fields. In other words, we're going to let F be a field, and I is going to be an ideal inside the field F. And the question is what, if anything, can we say about the set I? Well, I want to first of all start off by remembering that one thing that we know is that I could be the set containing just the zero element, or I could be the whole field, or the question is, I could possibly be something else, and the question is whether or not there's something else that I could be. Now, if I happens to be just the set containing the zero element, it's kind of a boring ideal. So what I want to do is I want to assume that I is not that particular ideal and see what I can say. So we're going to look at this situation. Suppose that our ideal is not the trivial ideal containing just the zero element. So what that says is there does exist somebody inside I with that somebody not being equal to the zero element of F. Now, since I is an ideal, I is also a subset of the field F, and hence A inside I implies A is also part of my field. And so I know that now A is a non-zero element of the field. So that says there is a multiplicative inverse inside the field F. So there's an A inverse such that A inverse times A equals A times A inverse equals the multiplicative identity of the field, in other words, 1 in F. And I really want to think about what that statement says, because in this statement, I have an element of my ideal times an element of the big ring / field F. And because I is an ideal, any element that is something in the big ring times something in the ideal is going to fall into the ideal. In other words, I want to look at this. I know that A belongs to my ideal, and I know that A inverse belongs to the field F. Hence, A inverse times A has to belong to the ideal, and that is because I is indeed an ideal. But we already know 1 is equal to A inverse times A. Hence, the multiplicative identity of the field has to belong to our ideal. And that actually is something that's worth stating as a formal lemma. In other words, we have just proved this particular lemma. If F is a field and I is an ideal of F, then I not being equal to the trivial ideal that contains just the zero will imply that the field's multiplicative identity, the 1 in F, belongs to I. And we just proved this. Well, what I now want to do is turn my attention to why is this lemma important. So let's continue investigating what's going on in this situation. In other words, let's let I be an ideal of field F, and I is going to be known to not be equal to the zero ideal. What can we say? about our ideal I? Well, the very first thing is we already know that since I is not the trivial ideal containing just the zero, the one inside the field does belong to our ideal F. Now look at this. Let F be any element of our field capital F. Times 1 has to be inside I because 1 is inside I and F is inside our big ring / field capital F, and I is an ideal. So what this says is that for every little guy inside our field, that little element F belongs to I. And that implies that F itself is a subset of I. And what I want to recall is that I is also a subset of F since I is an ideal of F. And an ideal, of course, is a subring, and a subring requires you to be a subset. So let's look at what we've got. We've got F as a subset of I, and I as a subset of F. Well, those two things together say that we can conclude that F and I are equal to each other. In other words, what we've shown is this theorem. So we have now proved this theorem. And this theorem is going to be stated as follows. Let F be a field, and I is an ideal of F. Then I is either the zero ideal, or I is all of F. In other words, what we've shown is that fields contain no improper ideals. Not improper. I should say no non-trivial ideals. The only ideals in a field are the trivial ideals. There are some important implications of this. So it's important to note, if you know I is an ideal of a field F, and you know I is not equal, let's get that notation correct. If you know I is not equal to all of F, then I has to be just the zero ideal. In other words, the only proper ideal of a field is the zero ideal. And this has one more implication that is worth noting. If we look at phi being a ring homomorphism from field F to any ring S, then we already know that the kernel of phi is an ideal of our field F, and hence one of two things happens. The kernel of phi is just the zero element of the field, which will imply that phi is 1 to 1, and that will mean that F is actually isomorphic to the image of phi, or the kernel of phi will be the whole kit and caboodle of the field F, and that will imply that phi taking F into S is given by the formula phi of little f is equal to the 0 in S for all F inside the field. In other words, in the second one, if this is F and this is S, and that's the 0 over here in S, the whole field gets sent to that one particular element. And that completes this particular video.